Welcome everyone. In this explainer, we're going to build a really solid framework for analyzing capacitor networks. We'll start from the very first principles and work our way up to some pretty advanced problem-solving strategies.
So, here's our game plan. First, we'll get a handle on the whole idea of equivalent capacitance. Then, we'll break down the two big configurations, series and parallel. After that, we'll mash them together to solve combination circuits. And finally, we'll go all the way, figuring out the specific charge and voltage on every single capacitor in a complex network. Let's get into it.
You know, the main goal when you're looking at a messy circuit is always simplification. The big idea is that any jumble of capacitors, no matter how complicated it looks, can basically be boiled down to act like one single equivalent capacitor. Our job is to figure out the capacitance of that one single component, and that all depends on how the originals were wired up.
Okay, let's start with our first fundamental model, connecting capacitors in series. If you can nail this down, you're on your way to tackling any circuit they throw at you.
So visually, a series connection just means they're lined up end to end. See here in diagram A, the negative plate of C1 is wired to the positive plate of C2, and so on. The really critical thing to notice is that this setup gives the charge only one single path to travel from the battery's positive side to its negative side.
Now this is the most important physical principle for series circuits, and it all comes down to conservation of charge. When you hook up the battery, it pulls some charge, let's call it negative Q, from that last plate and dumps a positive Q on the very first plate. This forces all the charges in those middle, isolated wire sections to rearrange. And since those middle sections started out electrically neutral, the charges have to balance out, which means every single capacitor in the line must hold the same magnitude of charge, Q.
So the charge is the same everywhere, but the voltage is a different story. Think of it like this. The total push from the battery has to be shared among all the capacitors in the line. According to Kirchhoff's voltage law, if you add up the voltage drops across each individual capacitor, it has to equal the total voltage of the battery. They split the total potential difference.
We can derive the formula for the equivalent capacitance, C sub S, right from that voltage rule. All we do is substitute our fundamental relationship, V equals Q over C, into each part of the equation. And here's the magic. Because the charge Q is the same for every single term, we can just divide it out. It cancels completely, leaving us with this really elegant reciprocal formula.
And applying it is just as straightforward. We just plug in our values, 1, 5, and 8 microfarads, into that reciprocal formula. Now, after you add up the reciprocals, you get this 1.325 number. But, and this is the step everyone forgets, you have to do one last thing. Flip it. You have to take the inverse to solve for C sub S, not 1 over C sub S. And that gives us our final answer. So, check out that result, 0.755 microfarad. That's smaller than our smallest capacitor, which was 1 microfarad. This isn't a coincidence. It's a universal rule for series circuits, and it's a great way to double-check your math. Here's why. Adding capacitors in series is kind of like taking a single capacitor and pulling its plates further apart. Increasing that distance always decreases the capacitance.
All right, let's pivot to the other main setup, the parallel combination. This one is all about giving the charge multiple paths to take, which is the exact opposite of the series case.
In a parallel circuit, you can see that all the positive plates are connected together to one common point, and all the negative plates are connected to another. This wiring structure means that every single capacitor is connected directly across the terminals of the battery.
And that direct connection is the whole key. Since every capacitor is wired to the exact same 2 points in the circuit, the positive and negative terminals of the battery, the potential difference, the voltage across each one must be identical. It's the same as the battery voltage V. That's the defining rule for parallel circuits.
Now, since there are multiple paths, the total charge that flows out of the battery gets split up among the different capacitors. It's like a river splitting into several streams. This is just conservation of charge at work. So the total charge stored in the whole network is just the sum of the charges stored on each individual capacitor. And of course, the bigger capacitors are going to hog a bigger share of that charge. The derivation here follows the same logic as the series one, but we start with our charge summation rule. Again, we substitute Q equals CV into each term, and this time, since the voltage V is the common factor for everything in parallel, we can just cancel it out from both sides, which leaves us with a beautifully simple sum for the equivalent capacitance, C sub P. So yeah, the calculation here is about as easy as it gets. You just add up the individual capacitances and you get 14.0 microfarads. This is the complete opposite of a series circuit, right? Adding capacitors in parallel always increases the total capacitance.
And that makes sense because you're basically just increasing the total surface area of the plates available to store charge. Okay, now for the fun part. Let's combine these two ideas. In the real world, circuits are rarely just one or the other. They're a mix. The key to not getting lost is to have a methodical strategy to break the complex network down piece by piece.
Step 1 is always to just scan the circuit and look for the simplest, most obvious combinations, the low-hanging fruit. In this diagram, it's pretty clear that capacitors C1 and C2 are connected end-to-end. That's a textbook series subnetwork right there. So we attack that part first. We calculate the equivalent capacitance for just that series pair using our reciprocal formula. This lets us redraw the circuit and replace C1 and C2 with one new single imaginary capacitor, which we'll call C sub S. You can see how that immediately simplifies the problem.
And what are we left with? Just a simple parallel circuit. We've got our new equivalent capacitor, C sub S, in parallel with the original C3. We know how to solve that, just add them up. This little cycle of identifying, calculating, and redrawing is the core strategy you'll use for any combination circuit. Okay, let's level up. So far, we've only cared about the total capacitance. But the much more complete and, frankly, more interesting problem is to figure out the specific charge and voltage for every single capacitor in the network. To do this, we need a two-pass approach.
Let's take a look at this network from example 8.7. Our first pass is all about reducing the circuit. We like to start from the inside and work our way out. Here, the most obvious first step is to see that C2 and C3 are in parallel. So we combine them into a single equivalent capacitor, C23, which simplifies our circuit into a basic series connection, as you see on the right.
This slide lays out the whole algorithm. So, pass 1 is reduction. We combine C2 and C3 in parallel. Then we combine that result with C1 in series. Now we have the total capacitance. Pass 2 is the expansion, where we work backward. First find the total charge the battery supplied, using Q total equals C total times V total. Now here's the key. Because C1 is in series with everything else, it has to hold that total charge, so Q1 is Q total. From there, we can find the voltage on C1. By our voltage rule, the rest of the 12 volts must be dropped across that C23 parallel block. And because they're in parallel, V2 and V3 are equal to that same voltage. Once we know the voltage across C2 and C3, we can find their individual charges. And as a final check, those two charges should add up to our Q total. It all has to fit together perfectly.
All right, now it's your turn to put this into practice. Here are 3 different network configurations. Each one uses the exact same strategies we've just covered, but you'll have to think carefully about the geometry and the right order of operations for each one. Take a close look at network C. It's definitely the most involved of the 3. It's going to take a couple of reduction steps. So before you even pick up a calculator, what's your plan of attack? What's the very first logical simplification you would make, and what does the circuit look like after you've made it? Think it through.